Okay, so that was some members of CASA. They don't get paid for this. They just do it because they really are super passionate about the program and the material, which is very unusual in my experience. They were a bit humble. They didn't mention that they organize a whole bunch of like really interesting big events. So not every year, but like they've run UTISM, the University of Toronto Interdisciplinary Symposium on Mind. They run like a variety of different like big conferences where they get big name speakers. So check these guys out. They really do. They're the most, as I think I said last time, the most energetic and interesting student group I've seen on campus. So yeah. Okay. Course business questions before we get into it. Anybody confused about where we're going and what we're doing? So if there's not, I'm going to start these classes off typically by doing a bit of review. So we'll just go over what we did last time, really light and fast. But this is also a good opportunity for you to ask questions that occurred to you maybe after class or during class you didn't stick your hand up. So we'll just go quickly over what we talked about last time and then dive into new material. Okay? Okay. Okay, so you might have been somewhat confused about what was going on last time because you walked into a class called Intro to Cognitive Science and I started throwing philosophy of science at you. You thought, that's not what I signed up for. Basically what we're trying to do last time is get a broad picture of what cognitive science is, but also try to get a picture of what its goals are. So what are the goals of cognitive science? And I offered you this sort of trite motto, this trite slogan, the interdisciplinary study of the mind. And we picked apart that slogan. We said, well, we are really quite unclear about what it means to be interdisciplinary, what the mind is, or in what sense we want to study it. So we spent quite a bit of time on that. And the conclusion that I tried to argue for was that this discipline is supposed to do this integration thing. So what we're aiming for is really a way of integrating these sub-disciplines into one unified discipline that can deal with the mind in depth. That was all that stuff. And then we started asking, in true style of philosophers, we started asking, well, what is integration anyway? What do you mean by integration? What's the point of integration? And I made this argument from Philip Kitcher that integration and explanation have something profound in common. That is, when you explain something, one of the things that you're doing is putting together both a whole bunch of different streams of evidence, that's the convergence of evidence, the multimodal sort of evidence stuff, and also we're trying to get multi-apt descriptions, that is, descriptions that apply to a whole bunch of different things. Closing the doors is a very good idea. So, and so this was one of our sort of like stage setting ideas. What we're going for in this interdisciplinary study of the mind is a plausible theory of the mind. We're just kind of setting the goals and standards for the discipline as a whole. And more specifically, we're trying to satisfy what's called the naturalistic imperative. This is Verveake. So the naturalistic imperative is something that Verveake put a name on, but really everybody in cognitive science is trying to achieve, which is to come up with a naturalistic account of the mind. That is an account of the mind that doesn't invoke spirit or like weird mental stuff, an account of the mind that we can fit into the scientific worldview. Because currently, as I argued last time, there's not a lot of room for the mind in the scientific worldview. Minds contain things like meanings and purposes, significance, relevance, all that stuff. And if you ask a physicist to tell you where the relevance is in the world, they will tell you that there's no such thing. There's protons and electrons, neutrons, there's basic elements. Those basic elements, there's no importance or goals in the basic stuff of the world. So our most fundamental accounts of the physical world include nothing resembling purposes or goals or importance or anything like that. But nonetheless, we all experience the world from behind our eyeballs where there very much is importance and relevance and goals and all that stuff, right? So our primary experience of ourselves is as agents who act in the world and care about that world, but that seems to have no place in the scientific worldview, or at least it's currently unclear how that fits into the scientific worldview. So the goal was to come up with an account of cognition that we can do the following three things to. We can analyze it, we can formalize it, and ultimately we can mechanize it in the sense of building a mind. That'll be our ultimate test for having succeeded in cognitive science, when we can figure out what the basic parts of cognition are, we can represent them in a clear, formal way, and use that representation to build a full-blown mind. So that's the goal. That was our basic laying out of the goals of cognitive science. That's what we were up to last time. How's that? Okay, good. So enough of that quick review. We're going to move on to hopefully more familiar kind of intellectual practices. We're going to start talking about categorization. Okay. So let's talk for just 1 second before we dive into categorization about analysis itself, the process of analyzing something. So what we would like as a first step is to analyze cognition. And this is an extremely normal way of proceeding in science. Generally speaking, how science works is you take something big and complex and slightly mystifying, and you break it down into its parts, into the simple parts that you can understand, right? What are the basic processes that underwrite this thing? Before we go on, I'd just like to point out the difference between having an analysis of something and having a true description. So it's much easier to come up with a true description of a phenomena than it is to come up with an analysis of it. Think of the sun, for example. We've had a bunch of true descriptions of the sun. It appears on that horizon and goes over the sky to that horizon, produces heat, produces light. Those are all true descriptions of the sun, right? And we as humanity have had access to those since probably as long as we could speak or think, right? So we've got true descriptions of the sun. When did we come up with an analysis in this sense of what's going on with the sun? Like pretty recently, right? We have an analysis of the sun now. Now we know that it's a fusion reaction. We know that it's mostly made of hydrogen, a little bit of helium and some other stuff. We know why it produces heat and light. We know the basic process by which it produces heat and light. So, and that was the last 100 years or so. I don't remember exactly when we figured that out, but it was the last 100 years or so that we worked out an analysis of the sun. Whereas before we had lots of true descriptions, but the basic processes were mysterious. So we've got lots of true descriptions of cognition. We know lots of things about the mind. Psychology has been doing pretty well at generating true descriptions about the mind. We know lots about the brain. We know lots about language. We know lots about culture. What we're lacking at the moment is an analysis of cognition. So an analysis where we try to figure out what's the most basic parts of this process. What's the simple bits that we can use to build up the rest of cognition, the whole complex phenomena out of these simple parts. So we're going to spend the first third or so of this course, the period before the first test, trying out various candidate things that we might analyze cognition in terms of. We've got a couple candidates we're going to try out. We're going to start with categorization. Maybe categorization is the basic mental process in terms of which we can understand all of the other mental processes. We're going to shift to memory. Maybe remembering things is the basic cognitive process. And then problem solving. We're going to test these out, and we're going to test them out not in the sense of doing experiments, but kind of looking at the history of the ideas about these things as people presented these processes as potentially basic, potentially the processes in terms of which we can understand the rest of cognition. And it's not going to work out. It's not going to work out for any of these processes in any clean or simple way. So we're going to do history of science. And history of science has a very different character than textbook science. I think it's rather unfair that they train scientists with textbooks and very little history of science, because textbooks are full of success. They give you the 1 in a million experiment that really worked well, and they leave out all the failure. And then you, the budding scientist, get into the lab and think, oh my God, nothing's working. This isn't at all like the textbooks, where you go from A to B and you generate knowledge and you win. That's generally speaking not how science works. Science, generally speaking, if you look at its history, which we'll start doing today, is a series of slight improvements in the degree of failure that you're experiencing. Basically, almost every theory fails. The goal is just to make your theory fail a little better. So that's one reason we're going to go through the history of science here. We're going to look at how scientists have been struggling towards trying to generate an analysis of cognition. The other reason we're going to go through this has to do with the kind of overarching argument of the course. So recall I mentioned very briefly last time, the overarching argument of this course is going to be something like this, or the conclusion of that argument is going to be something like this. The ability to figure out what's relevant is key to cognition. That you're never going to understand cognition unless you understand how we figure out what's important. So caring about the world is inseparable from being intelligent in the human sense of intelligence. And we're going to see throughout this lecture, and really throughout this whole first section, and again in the artificial intelligence section, that people have been not aware enough of the issue of working out what's relevant. So that'll be in here as well. Okay, any questions so far? Okay. So let's talk about this. So the place we're going to start, here's our potential basic cognitive process, categorization. Maybe we can, if we figure out categorization, we can use that understanding to apply it to all of the other mysteries of cognition. That's a reasonable place to start, I would propose. So just to sharpen up the topic of conversation a little, let's distinguish categories from classes or sets. So here's a really nice category, mammals. We're all familiar with mammals. You are all mammals. Mammals do things like give birth to live young. They typically are breastfed. You know, we have fur, that kind of thing. We're warm-blooded. Mammals. You've met mammals. Okay. So that's a category. It's a category in the sense that there's something that makes these things all hang nicely together. There's a commonality between them. A category is a unified group. Contrast that with a class or a set. If you've done set theory, you're familiar with sets. So here's a perfectly good set. There's Jupiter, a martini, a parrot talking into a microphone, and a croc. That's a perfectly good set. You can make a set out of anything. Any group of objects that you put together can be a set. There's no requirement that a set or a class be internally unified or structured in any way, right? So our topic today is categories, not sets or classes, okay? So what we're going to try to figure out is the human ability to put things into sets or classes that are actually unified in some interesting and important way. And there's an important reason why we want to focus on that, because categorization is crucially important. And let me give you a brief argument for why you should think categorization might be a basic cognitive process. Specifically, categorization lets you code your experience. Categorization lets you structure your experience. So just take a minute to imagine what it would be like if you had to experience every object in your environment as a unique individual. It would be hell. So this is a chair. I'm familiar with the properties of chairs. For example, I expect that if I touch it, it will not turn into a liquid. I expect that it's non-living. I expect that it's the property of somebody. I have all of these encoded expectations about what chairs are going to be like because I have a category of chair, right? Imagine if you had no category for fire and that a fire broke out. What would you, like, you would like to tell the people around you that there's danger. You'd say there's a fire, and they'd say, what's that? You wouldn't even be able to tell that it was dangerous until you stuck your hand in it, right? If you have to encounter every individual as an individual, you can't infer from your knowledge of having burned yourself as a child that this fire is dangerous, right? So your ability to make inferences from past experience to current situations crucially depends on your ability to categorize things, and much more than just put things in sets, right? Because a set doesn't tell you that the things are similar in any way, whereas a category facilitates inference. Yeah?
Would it be accurate to say the category is like a schema?
We're gonna, okay, that's, so I suppose it depends on what you mean by schema, but like, that's the debate for today. Like how are we gonna describe what a category is? Yeah, yeah. Right, sorry, I keep going ahead of my slides. So this thing, you need categories in order to not only make inferences from past experience to future experience, you need them to communicate your experience. You need categories all over the place, all over the place. Here's a really impressive one. So on the topic of using categories to make inferences. So here's a fact, here's a science fact. Flamingos have right aorta hearts. That is, the aorta on their heart, one of those major tubes, goes on the right. Here's another science fact. Bats have left aorta hearts. Their aorta's on the left side. Okay, so now, what kind of hearts do you think sparrows have? Right. That is both right and correct. Yes. Sparrows have right aorta hearts. Now, how did you do that? Yeah, yeah. Very good. Yeah, so what you did is you relied on your knowledge that sparrows and flamingos fall into the same category, right? If something is a category, it's got unified properties. It's got properties that you can say, if the category's got this property, then any member of that category's got that property, right? This is how categories play in inference. Okay, so, and look what you did in order to make that inference. So I propose that the bat looks a lot more like the sparrow than the flamingo looks like either of them, right? So if you're just going by the surface features of the thing, like I would have, if you're just talking about the broad perceptual features, like bats are small, sparrows are small, bats are kind of brownish, sparrows are kind of brownish, right? So if you're going just by the surface perceptual features of things, rather than the categorization that you use to understand the world, you would have got this wrong. By the way, 4-year-olds can do this. So it's not just that we are super sophisticated, intelligent people. Well, of course we all are, don't worry, but like, it's that we've got this really built into us. Categorization seems to be something that children are perfectly able to do. We start doing it really young, and it seems to underwrite huge amounts of what we're able to do as intelligent agents. Yeah? Yeah?
How would this work with respect to kind of unlabeled data? If you had no kind of frame of reference of what a flamingo was or what a sparrow was, like they both perhaps maybe have features or similarities of each other, and you don't have a category to work with, how would you kind of decide, or how the process would work that the sparrow could be deduced to have a right aorta heart?
Well, so you need the category birds and mammals in order to make that inference, right? If you don't have a category, you typically need to generate one. So, and people are very seldomly at a loss for coming up with a category for an object, right? So we will almost like uncategorized experience is very rare. Any object that you look at, try this in your environment. Is there anything that you can fail to categorize in your environment? I doubt it. I doubt it. Right? You'll come up with some kind of category or other. So, and we do it unconsciously and really quickly. So anything you encounter, you'll stick it in a category. The question is it the right category? Is it the relevant category? Is it a good category? Those are all like, you know, the imperfections of human cognition, but we very rarely fail to we very rarely fail to have, as you say, completely unlabeled data as perceivers of the world, which is another perhaps small argument for the belief that this is all, by the way, if you recall, this is all in service of the argument that maybe categorization is a basic cognitive process in terms of which we're going to analyze all of our other cognitive processes. Okay. So I just want to point out, none of that was a proof. That was a pretty, honestly, that was a pretty flimsy argument for categorization as, so you shouldn't have come away from that argument being, I'm convinced categorization is it, right? What I showed you was hopefully that it's important, that it's a deep part of like our cognitive lives. You couldn't do without it. It would be extremely inconvenient to be a non-categorizer in the world. None of that proves that it's the basic cognitive process, but we're really just trying to get our feet under us right now. We're really just trying to get the project going. So if something shows promise as a candidate, it's worth investigating. That was the argument, the conclusion of that argument, a reasonable conclusion of that argument is just, categorization's worth a shot. So let's give it a shot, shall we? Okay. Okay. So let's get into it then. So I'd like you to give me just your off-the-cuff, spontaneous, intuitive response. How do we categorize things? Yeah. Shape is a really good one. Yeah. Anything else? How we sense them. Yeah. Sensory properties. Yeah. Functions, perhaps. Yeah.
What other people tell us about them?
Yes, yes, absolutely. Yes. Yes, so our beliefs, our knowledge. Okay, so those are all sources of information about how we categorize. What is it that we do with those sources of information? How do you use those sources of information to come up with a scheme for categorization? Yeah. Good. So we ask about whether the features of those things match each other. We ask whether, I would propose, that they're similar or not. Yeah? So one really nice intuitive answer to this question. So you're all absolutely right about where do you get information about how to categorize, where do you get the raw data? And then once you have that raw data, the question is what do you do with it? And one really perfectly sensible sounding answer is we judge things on terms of their similarity. If things are similar enough, we group them together into a category. And if they're dissimilar, we put them in separate categories. Yeah? Yeah. So this was like similarity-based accounts of categorization are basically what we're going to do for the rest of the day. And there was a long tradition in the psychology of cognitive psychology trying to get this going, trying to get similarity-based accounts of categorization to account for our ability to categorize and hopefully use that as an analysis for the rest of cognition. And the hope was that similarity would just kind of be a fact in the world. That similarity was something that you could measure as an objective fact, like weight or size or shape. Right? Those are all of those things. Like there's a fact of the matter about whether something's a sphere or not. There's a fact of the matter about how much an object weighs in a given gravitational field. Right? So you can just measure those things. And the hope was similarity would be like that. And similarity is an objective fact about a set of objects. And if that's true, then you can teach a computer how to judge similarity, right? You tell it what features to look at, how much to weigh those features, and then it's categorizing in the way we do. And we're off to the races. That turns out to be a problematic assumption. That turns out to be an assumption that doesn't pan out. Similarity is a lot more complex, and we'll spend most of the rest of this class talking about this. Similarity turns out to be a really tricky problem or property to pin down. Let's do some, I know you're all pining for the days when we did lots of philosophy, so let's do some philosophy. The philosopher Nelson Goodman has a critique of similarity. Critique of similarity as a way of doing categorization. So he says the following. He says, similarity is partial identity. Partial identity. Two things are identical, of course, if they share all of their properties. If you say A has this list of properties and B has the exact same list, then those two things are the same, right? That's Leibniz's law for you philosophers in the room. So similarity is just sharing some subset of your properties. I'm similar to my brother because we have a whole bunch of properties in common, not all of them, but a whole bunch of them. The problem is, how many properties does any given thing have? How many properties do an apricot and a lawnmower share? What are some properties that an apricot and a lawnmower share? Yeah.
Solid.
They're both solids. Very good. Yeah.
They can both roll.
They can roll. Either could roll. Yeah. They're both smaller than the planet Venus. They both make fairly ineffective siege weapons. Yeah.
They're both sold.
They're both sold. Yes, you can buy either of them. Both are common in North America. Neither of them fend off vampires. Yeah.
Just have a thinking non-similarity, depending on which questions you ask, will satisfy either condition.
Right. Right. So yeah, exactly. Goodman's claim is that if you start getting creative about thinking about the properties of things, usually we fix it. We're practically minded animals, very sensibly so. We usually focus in on the important properties. This one's food. This one's a tool, right? But if you start getting creative, any object has an infinite list of properties. Any two objects will have an infinite list of shared properties and an infinite list of non-shared properties. So if your metric of similarity is how many properties do they share, how many properties do they have in common, well, any two objects share infinitely many properties. So just sharing features, I've just given you an argument that just sharing features cannot be the way that we assess the similarity of things. Yeah. Now, we're going to nonetheless see some very smart cognitive psychologists attempting to build an account of categorization based on similarity, based on feature lists. It's not going to work out, but we can already see that hopefully philosophy can contribute a little something to this project. So thinking about our naive assessments. Okay. So we also, there's another interesting fact about similarity that makes it increasingly clear that it's not just a thing in the world. Like, there's no similarity-omometer, right? There's nothing that you can, there's no objective fact of the matter about how similar two things are. You can tell this is the past one was a philosophy argument. Here's one from psychology on ad hoc categories. The fact is that we don't just have a fixed set of categories that we operate with. We are perfectly capable as humans of generating new categories on the fly as necessary. So here's a group of things. Here's a category: spouse, children, pets, works of art, explosive or toxic material. Is that a good category? Does that hang together for you? What about things you should be worried about when your house is on fire? Now it's a category, right? So hopefully your house being on fire is not a situation that's ever happened to you. Hopefully it never happens to you. Hopefully it's not common in your life. But nonetheless, you can generate a category for that very weird scenario immediately. Furthermore, the categories that people generate seem to be relative to their goals, what you care about, what you're interested in, which is by no means a fixed property of you. One of the most beautiful and marvelous things about you is that you can change your goals. Your goals are constantly changing over your lifetime, and if your goals are changing, that actually turns out to entail that the categories that you operate with are themselves changing. So if similarity is out there in the world as a feature of objects, and we categorize based on similarity, that shouldn't be true, right? Yeah.
Couldn't you argue that those goals or contexts are categories in and of themselves? And then you have the thing we were talking about last class about the homunculus, where the guy, so you need another category, how that category run into their own kind of a bunch of categories defining
I think a goal is different than a category. I think a goal is different than a category. So a category is a way of placing things either in a group or out of a group, whereas a goal, like a goal is something that's important to you or that you want, right? Like it has a different cognitive role, I would suggest, than a category. In some sense, it's okay to have, and furthermore, I think it's okay to have an infinite hierarchy of categories. You can have categories of categories of categories of categories, and so long as you don't, as a matter of fact, actually have to think through them all, that's kind of okay. Set theory lets us do this. I don't see any reason why we shouldn't be allowed to do it either. So, yeah. Okay. Any other questions about this stuff? Or comments or criticisms? Again, this is typically during the regular semester, this is a 2-hour class and you have 1 hour of tutorial. So we're kind of rolling tutorial into this class. So, yeah.
So if your goals can change, then this like same set of things can be a different category.
That's right, yeah. If you don't have the goal of getting your precious loved ones and objects out of your house, this isn't really a good category. And as soon as that's your goal, then it becomes a category. And as soon as you've done that, it kind of falls apart again. Unless there's another, I don't know. It's the only one I can think of for this one, but yeah. Yeah, so what strikes you as a category is going to change over time as your goals change. Which again, is very undermining to the kind of simplest, naive view of categorization, which is just that you see some objects, you size them up, you figure out what their properties are, and if they share enough properties, that's your category. No. Part of why this is a tempting view is because all that stuff happens in the background of your awareness, doesn't it? Like you don't have a conscious experience of your brain going, well, my goals today are thus and so, therefore, these are the salient categories for my day, right? That's not how your experience is. If it is, I would like to talk to you after class. That's not, generally speaking, that's not how your experience is structured, right? What you experience is just, that's a chair, that's a table, that's a bottle. Those are people, right? The world appears to you pre-labeled because your brain's doing all this work in the background and not telling you about it. And be grateful that it does. You don't have time for all that, right? Be grateful that your brain is doing this unconsciously. But what that means is when you're introspecting, when you're thinking about your own experience, all you see is, well, things come together in categories. That's just how they come. That's just how they are. So if you're trying to be a psychologist or a cognitive scientist, your introspection is going to mislead you about the structure of this process. And let me show you an example of that actually happening in practice. So we're going to talk about resemblance theory. So this is from the reading from today, Smith, 1995. It's a great reading. Smith is a really smart guy making a serious attempt to understand categorization, hopefully, and he's doing it in the tradition of cognitive science, so he's advancing this as potentially a way of understanding all of cognition. And he says the following: judgments of resemblance drive our judgments of categorization. That's the essential thought of the resemblance theory. And I've already given you, I've pre-ruined this theory for you by giving you the objections before the theory, but we're going to go through the details of the theory and then object again even harder. Okay. Okay. So, really quickly, just a so hopefully this is a clear idea to you now. Hopefully the idea that's being presented is at least relatively, like, you get the gist of it. We'll go to the details in a minute, but hopefully you get the gist of this, where he thinks that what we do is we look at the world, we pick out an object, we figure out what its properties or features are, and then we use that list of properties or features to figure out, well, is this object got enough shared properties with this object? Does it resemble it enough to count them as belonging to the same category? Yeah. Okay, so a real quick objection, just to keep the objections flowing, from Lance Rips, who has possibly the greatest name in the history of psychology. Here's just a quick example of, so the theory is, the theory is judgments of resemblance drive judgments of categorization. So the basic process is figuring out the resemblance of things, and that's what generates our judgments about categorization, then categorization underwrites inference, so on. Rips says, yeah, but look, sometimes categorization drives our similarity judgments. Categorization can make us think that things are similar that you wouldn't normally think of as similar. Take, for example, light, sound, and water. If you told somebody 300 years ago that these things are deeply similar, they would have looked at you funny. They would have said, have you ever taken a nice dip in sound? Have you ever lit a room with water? What are you talking about? Those are very different. But now we have a wave theory of light, a wave theory of sound, and obviously water can undergo waves. So now we know that there's this deep similarity between water, sound, and light. They all propagate waves to themselves. So having this category, things that are wave-like, allows us to see the similarity in a way that people who had just had the exact same sensory experiences of light, sound, and water as we do. I don't think there's any big change in the sense data that comes at you from these three sources since the last couple hundred years. What's changed is the way that we categorize things. We have a scientific theory of light, sound, an understanding of wave dynamics, and that theory makes you experience these things as similar or more similar than you would have if it wasn't for those categorization judgments. So if Smith is telling us the basic thing is resemblance, perceptual resemblance, that drives categorization, Rips is saying, no, look, here's an example of categorization judgments driving judgments of similarity. Right? So the way that you categorize things can make you experience them as more similar or different. Think back to the flamingo and the sparrow, right? How did we understand that the large pink leggy bird is more similar to the small brown round bird than the bat was? It's because you have this category of birds and mammals, right? That's what drove that. So categorization judgments overriding perceptual similarity judgments. So already that's going to be a problem. It's going to be tricky for Smith to defend the resemblance theory of categorization. So let's talk about some attempts to formalize similarity judgments such that we can use those formal analyses of similarity to build a model of categorization and therefore start the process of analyzing cognition. So here's a really old one. We're going to go way back. This is from the 60s, early 60s. It's called the geometric account of similarity. So I put the reference on there if you want to take a look. Basically what they did was the following. Got a bunch of people in to the lab and asked them for similarity judgments about various things. So here's a graph showing how similar people thought various fruits were. And you basically just ask them a series of questions. How similar do you think apples and grapes are? Give them a number. How similar do you think peaches and pears are? Give them a number. and make a bunch of lists of these things, and then they would use those, they'd put those lists through an algorithm and generate a 2D map of their similarity judgments. And the idea was just that maybe here's how people deal with categorization, deal with similarity, that you have a kind of space, they assumed a 2D space here, where you would place the various types of things. And so here's the category. Basically, this is a map of the category of fruits, all of the different types of fruits. And when you're categorizing, what you do is basically drawing a kind of arbitrary circle around the prototype. So there's fruit in the middle. So you say, how typical is an apple as a fruit? And if it falls within a kind of radius of typicality, then that's your category. That should make at least some intuitive sense, right? So sometimes when you're making categorization judgments, you don't say yes or no, right? So is tomato a fruit? You go, sort of, right? So we make these kind of sort of judgments all the time, right? You don't always have a crisp, clear way of categorizing something. Say of a movie, is this a rom-com? You go, well, right? So categorization judgments often come by degrees, right? They're not crisp and clear. So maybe it's just like this. Maybe what we have is judgments of similarity that can be laid out in a systematic way, and then you roughly just sort of draw a circle around the prototype, and that's how you do categorization. So great. This makes a bunch of predictions. So it's a way of formalizing, at minimum, what we've got here is a way of formalizing people's similarity judgments, right? We've laid them out formally in the sense that we've given precise quantitative and geometric sort of like representations of similarity judgments. So it's a start, right? We're trying to formalize similarity. As described in the Smith reading, so the Smith reading takes this up and sort of critiques it quite significantly, points out a bunch of, some of these are very weird problems. Sorry, yeah, a question up there.
Like not fall to the issue of kind of overfitting in this case. So, okay, I have a bunch of people that have all come to the same conclusion that these things are separated by this one algorithm, think the same conclusion that they're separated by this, but it's missing some information that could be relevant, that could geometrically structure the information differently. You're not operating with a full set of knowledge effectively.
I think they just didn't solve that problem. I don't think that they solved that problem, yeah. Because this is an average over the group, right? So different people will give slightly different judgments, and basically they just aggregated the data and made an average. It was the 60s, come on. They're just getting their ball rolling here. There are a number of kind of deep problems with this, deep empirical problems where this way of formalizing similarity just doesn't match how people actually do it. People make really strange judgments about how similar things are, and they don't fit the predictions of this model. So this model makes a bunch of predictions, a bunch of very sensible sounding predictions. For example, symmetry. If I say A is 50% similar to B, I should say that B is 50% similar to A. That's just how geometry works, right? So if you're saying similarity judgments are laid out on a 2D geometrical plane, then it should have this similarity or this symmetry property. But people don't judge similarity like that. If you ask people, how similar is Taiwan to China, they'll say it's very similar. And then if you ask those same people, how similar is China to Taiwan, they'll say, it's not that similar. How similar are lemons to apples? Not pretty similar. How similar are apples to lemons? Not that similar. So people are making asymmetrical judgments about similarity. It's a prediction of the model. They should make perfectly symmetrical judgments. As a matter of fact, they make asymmetrical judgments. Here's a weirder one. Minimality. So this model predicts, and any sensible person presumably would predict. If I ask you how similar are pairs to pairs, you should say all the way similar. That's as similar as anything can be. That's completely similar. But that's not what people do when you sit them down in a psych experiment. If you ask them how similar are apples to apples, they go 100%. Apples, totally similar. Okay, how similar are pineapples to pineapples? 90%. They won't make the same judgments of similarity from things to themselves. The more typical something is, the more common or familiar it is, the more people will judge it as highly similar to itself. And that sounds baffling, right? Utterly baffling. And it's there's one more property that this makes, prediction that this makes that is too finicky and technical to get into. That's in the Smith reading if you're curious. Basically, it's that the shortest distance between any two things should be a straight line, and people don't obey that one either. Okay. So the geometric account of similarity, it's making good predictions, which is one of the reasons why you want to formalize your theory, right? That's one of the reasons why you want to build a formal description of whatever phenomena you're trying to understand so that you can use it to make predictions, and then some smart aleck comes along 5 years later to show you that you're wrong. But being wrong is not a problem. Being wrong in intelligent ways is the best any of us can hope for. I once had a relatively famous philosopher come up to me after I'd given a paper at a conference. He says, "I think that your paper was interestingly wrong." I'm like, yes, yes. That's as good as I could have hoped for. Okay. So, but we okay with this? We were like, this was an attempt to formalize similarity judgments. It made some predictions, and those predictions just turned out to be incorrect. As when you measure what people do, they just don't behave the way that this predicts they should. Yeah? So let's do better. See if we can do better. Yeah? So here is Tversky's formal account of similarity. This is picked up by Smith in the reading, presents this as a way of formalizing similarity judgments. So the similarity of I to J. Actually, if you're frantically writing this down, just wait 1 second. Here's a visual representation from the Tversky paper. So the similarity of A to B. I've changed it from I to J to A to B to match the figure from the paper. So the similarity of A to B is given by the following three things, roughly. The shared properties of A and B minus the properties that B has that A doesn't, minus the properties that A has that B doesn't. Yeah? So similarity is how many properties do you share minus how many properties do you don't share. Modulated by a couple of things. There's a couple more things to, so that's the intuitive picture. There's a couple little things here like A, B, and C, which are coefficients that tell you how much weight you put on each of them. So in some contexts, you might care a lot about the overlap and not so much about the differences. In some cases, you might care a lot about the differences and not so much about the overlap, right? So those are ways of differentially weighting how much you care about one or the other parts of them. And there's also F. So F is a function that applies to each of the properties that are being summed up here. And it multiplies the number of properties, or the property by how salient you think that property is. So if you've got overlap in really important, salience is like importance or relevance or how much it jumps out at you. Perceptual salience typically means like how much does it jump out at you. So if a fire alarm goes off, it's very salient because it grabs your attention, right? So the similarity of two things is given by the coefficient of how much you care about their overlap times the salience of each of the properties in the list, in the overlap, minus coefficient of the non-overlap times the salience of each property that doesn't overlap, minus coefficient salience non-overlap. Yeah? Okay. So this is, again, it's a separate formal attempt to formalize similarity judgments. And presumably, we're talking about categorization. If the similarity of I to J is above some threshold, then you say, yeah, those two things are collected together into a category. If it's below that threshold, you say, no, these belong in different categories. Yeah? What do you think? Terrible. Okay. I couldn't have done this. This is better than I would have come up with. Yeah.
It's a good attempt. I don't know, A, B, and C are too vague for me.
A, B, and C are quite vague. A, B, and C are challenging to specify because how much do you care about those things? F is going to turn out to be a bit of a trick as well. F is going to turn out to be extremely challenging to nail down. Well,
How does one kind of take their mind or their own personal opinion and perception of something away from this and find that this is how much it jumps out, not to mean to everyone, this is how much weight that this should be given, not to mean to everyone.
so, I mean, it's a good question. In some sense, we don't, because we're precisely dealing with cognition, we're dealing with the mind, it's neither necessary nor helpful to be objective. In some sense, what we might want is, so here's perhaps an ideal situation for this theory. Suppose this theory's got no problems. Suppose it's like the end of the story about similarity and categorization. Presumably, you have judgments in a specific context about how important the overlap is, how important the non-overlap is, and how important each of the features are. So if you say, you know, are these two movies the same type of movies? You might care like, well, is there a romantic subplot or isn't there? That's what makes it a rom-com. If there's no romantic subplot, then that's not a rom-com. So for you, there's various salience of the properties. So it doesn't need to be the case that there's one unified story about how salient everybody finds something, or there doesn't need to be the case that there's just one answer to have the values of those coefficients. Those coefficients could change over time. Tversky actually tries to answer the salience question a little bit. He says things like, of geometric figures, if it's a well-formed figure, people find it more salient. Or if it's bright and flashy, people find it more salient. I find his answers to be pretty profoundly unsatisfying, but he does attempt to give answers to that kind of thing. He thinks that there are, like for baseline perceptual salience, there are some commonalities, right? So I don't know anybody who, if they smash their toe on a coffee table, aren't quite gripped by that for a couple of seconds, right? So pain is hypersalient, loud noise is hypersalient, bad smells are hypersalient, right? So there are some regularities about what grips our attention. But if the question is, how do we nail down like the salience of very fine-grained small categories, I think we don't need to, because people actually, as a matter of fact, people do categorize things differently. So a full account of our capacity for categorization should include that fact, right? It shouldn't wash it over. So if your theory says people will make the same categorization judgments everywhere, and people do different categorization judgments, that's a problem for your theory. So in some sense, we don't want this to be objective. We don't want it to be just like a blanket statement that applies to everything. We want it to be sensitive to the individual differences. Is that good? Okay. Yeah.
But so if you're formalizing it in a way through an equation,
Yeah.
then you're assuming that equation should hold the same weight from like space A to space B, right? But if you're not being objective, then for instance, if you have the two same objects and then there's two different people, and the valence of each like A, B, or C or whatever is different for you and I, then if you get two different things for that equation for the same two objects, don't you run into a problem with the equation itself?
Well, no, because these are so A, B, and C, for example, are variables. And basically what you can do is, so long as the equation holds, if I have a different value for A than you do, because I care more about the overlap than you do, then the equation's still true for both of us. right? The equation is still, the balance of the equation is still holding, assuming, because, you know, just like any variable, like these things can change, and presumably they would change over time. They change as your goals and opinions shift, that kind of thing, right? So if I'm making different categorization judgments than you are, which is a totally normal thing to happen, this equation can still be true of both of us, so long as you plug in different values for the different coefficients. Yeah? Like, it should capture, a good theory of categorization should capture both the similarities and the differences between people's judgments, because we really do make a bunch of different judgments. Yeah?
I think the biggest problem with this formula is that none of those sets are finite sets. You can't,
Yeah.
like you mentioned before, there can be infinite number of similarities and differences. So it really doesn't do anything.
It's a problem. But do you have thoughts on that?
F solve that?
F as the relevance. So.
But F is the function. The sets are the inputs. Like you can't, unless you want to be very mathematical about it and solve like the infinites.
Can I respond on your behalf? So we with the apricot and the lawnmower thing, right? So we've got this list. We've got infinite lists of things they have in common. Both are smaller than Venus. Presumably, the F for that would be very, very low. We could maybe even set it to 0. So how important is it that when you're trying to categorize the world, you're trying to get through your day, you ask yourself, apricot, lawnmower, are those the same kind of thing? The relevance of size relative to Venus is, you might even set that all the way to 0. Right? That could go to 0, in which case, the fact that they're an infinite number maybe doesn't matter if there's only an infinitesimal number of relevant ones. So you could be a finite list of relevant properties, the kind of properties that normal non-philosophy people produce. When you say, what are the properties of an apricot? You say, well, it's round, it's food, it's delicious, it's got a pit. So that might be a finite list, whereas the infinite list is filled with almost entirely irrelevant properties. Maybe that's one way of, is that kind of the thought behind that? Yeah, good. Yeah, another question.
Just even the idea about properties, we're gonna like connect this back to like similarity being important to categorization, categorization being kind of the crux of cognition.
Yeah.
So when you look at any like property or attribute, you're also in a way kind of making it a category as well, right?
Right. Right.
All right, like how many, like this might be brown and that might be brown.
Right. Right.
But the brown itself becomes the category. So like.
Yeah. So that's sorry, go ahead. Sorry.
No, it just seems.
There's a danger of circularity, but I believe the thought is the following, that at some point you get down to what they call perceptual primitives. So like at some point you get down to we have perceptual limits on how small of a difference you can observe between two colors, right? So like there's a minimum distance in color space. And you might say, look, blue is the region from here to here in color space. That kind of makes it a category, but you can get down to like perceptual atoms is the thought, that there's a like really basic, like one nerve firing in your optical nerve is the kind of minimum unit of perception. And then that itself is not a category, it's just the raw data that you're working with. So I think the thought is, or the assumption is, that at some point you get down to raw data that is not itself a category, they're just simply individuals. We'll see that later, much later in the course, we'll see some reasons to question that as a picture of how our senses work. But I think that's the assumption is that you get down to like, you know, and there is, in visual processing particularly, there's not terrible evidence that we do stuff like, here is an edge, like I see an edge there, and that's not a category, it's just like a thing that happens in your eyeballs, and we can say which nerves are involved in that kind of thing. So I think that's the belief. Yeah.
One of the issues, like in terms of similarity, if I had, let's say, a blind man that could only be described things and didn't have a sense of touch, and I wanted to explain to him a circle, I'd have to painstakingly describe a circle to him, versus let's say a man that could only, I don't know, see things but had no touch, no hearing, and I showed him a picture of a circle. We know like these two things are a circle, but like the information or the similarity, the link between them is different. Each person is going to weigh those features of what a circle is differently. How does this kind of stand up to one's individual or perception of the context of something that they can frame it?
First, blind people know what circles are.
Well, I'm saying
Okay.
they know what
Okay.
circles are.
Okay.
I'm saying
Okay.
their perception of a circle or their features or their importance or weighting of how they define a circle is vastly different than, say, a person that has sight
Yep.
or,
Yep.
or has that knowledge or input, if you will. Like how
But why is that a problem here?
they both see a circle. They can both categorize it as a circle.
Uh-huh.
It's in that. But their weighting of the features of that are completely different. One doesn't exist to another.
But again, why is that a problem here?
Then how can we come up with any proper categorization of any object if like the features that we use to describe it can just be all really?
Well, we all come up with, well, I mean, we have a lot of shared categorization, but people will categorize things differently. Again, so as a matter of fact, we have a lot of shared categories. Typically, we get taught how categories work, just in the scenario, like in the scenario you described. But there's nothing, I don't think our theory should rule out differences in categorization. For example, if you have radically different sense data to work with. So if you've got somebody who can't see but can hear and somebody who can't hear but can see, they would probably categorize the world in different ways. Blind people report that it's one of the nicest things about being blind, that you don't judge people by their appearance. So people who can see judge people by their appearance, by and large. Blind people don't. So it's a different way of categorizing the world. People with appealing voices, maybe, rather than appealing faces or something like that. And that's certainly not something that you want your theory to wash out. You want your theory to be able to capture that kind of difference, right?
I guess like the features, or like the weighting of the features, like a person won't have that feature with how they're making similarity or something. It's not there. They haven't perceived it.
Yeah.
It's never introduced.
Yeah, so they'll make different categorization judgments. And that's, I mean, what you're saying is true, but the conclusion of that argument is just that people will differ in the way they categorize things, and as a matter of fact, that they do. So it's not a flaw in the theory that it predicts that people will categorize differently, because we do. Okay, yeah.
For like the variables, do
Yep.
they hold true for like all the things in those sets?
Ah.
Would like A be different for like one similarity versus another similarity? Because here it's on like.
I believe it holds for the whole set.
Wouldn't like one similarity differ in importance than like another similarity?
Yeah, you might get that by F. So F is the salience. So you might say, by rating it, by saying this is the feature that I care most about, it's got a very high F.
Well, that differs.
That differs by, yeah, that differs by, so it's a function that applies to each of the properties in those sets, in those unions or disunions. Yeah, yeah. Okay, let me try to make this theory at least a little bit appealing to you, because we've been worried deeply about it, and I know I presented this as we're just gonna trash this thing, but it actually does solve some problems for us. It actually helps us to improve some of the problems, at least from the geometric account that came from before it. It explains some of the very weird properties of people's judgments of similarity, at least. So, the minimality problem. Remember that really weird fact that people judge apples more similar to themselves than they do pineapples? That's really weird. This can actually explain that. So, based on really bizarre psych experiments where they just have people, they'll sit you down, this was in the 80s, they sat you down and asked you to list all of the features of apples you could think of. And you think, I'm getting paid $5 for this? Okay, so suppose that you sat somebody down and say, name all the properties of apples you can think of. Here's just a small sample, but because you're familiar with apples, assuming that you're familiar with apples, you say round, red, crunchy, grows on trees, has seeds. So you know a bunch of stuff about apples. You got a bunch of features that sort of jump out at you. Presumably these people were not being like us. They weren't trained in philosophy, so they didn't say ridiculous stuff like is not a number or whatever. They just acted like regular people. And then ask them about something that they're less familiar with, they'll produce less features, right? They'll have a shorter list of features that they think of, that they associate with that thing. Okay, so let's look at what happens in this metric. So you're asking similarity of A union B minus the dissimilarities. If the list of things in the so here A is just the union of A and A, but if you got more things in that list, the number goes up. Yeah, the more you know about the thing, the more similar this actually predicts that the more you know about something, the more similar you'll find it to itself, because in that union there's a larger number of properties. You know more about apples, you know more about where they come from, you have more spontaneous associations with them. So when you ask how similar they are to themselves, this equation actually predicts that you'll say apples are more similar to themselves than apricots are to themselves. That's pretty good, right? Interesting, at least. Yeah.
What about something that's very familiar but very simple, like a circle?
So you'd have to compare it to something that's less familiar, like a rhomboid. I don't even remember what a rhomboid is. It's just the first unfamiliar geometric shape I could think of. So I can think of I have lots of associations with circles, despite the fact that they're very simple. So while they're round, they show up a lot in nature, apple-shaped. You could probably rhyme off, for a familiar geometric simple shape, you could probably rhyme off more properties than you could for, again, does anybody know what a rhomboid is? Because it's killing me now that I can't remember what it is. Yeah, so I have right now I can produce I know it's a geometric figure. That's all I got. That's all I got. So if I was producing a list of properties of rhomboids, that would be a very short list for me. Whereas circle, do you have is somebody looking this up for me? Come on, you've all got smartphones. Yeah. Parallelogram, okay. Oh yeah, okay, yeah, or like yeah. It's got two parallel sides and then two other parallel sides. Okay, good. Okay, so, yeah.
But then couldn't you also get the problem where like two rhomboids are not as similar as apples are to apricots?
So it's possible. It is possible, depending on how many features you've got under this lists, right? So if you got very short lists for both apples and apricots, and their disunion is very small, then you potentially could, yeah. That's a weird feature of this thing. But again, people make really weird judgments about this. So I don't think anybody's done a study on whether you can generate that quite counterintuitive result. But just what we need is a theory of cognition that captures not just the parts of cognition that make sense. We make all kinds of bizarre judgments. We do really weird stuff, especially when we're put in the artificial environment of a psych experiment. So what we want is a theory of cognition that reproduces not just our successes, but our errors as well. That's how you know that you've got actually how we're doing it, rather than just something that's smart in a different way than us. If your project is to figure out how we think, you want it to produce our successes and our errors. So if the theory predicts that we make this really weird judgment that rhomboids are less similar to themselves than apples are to apricots, and then you get people to do that in the lab, that would be a stunning confirmation of the theory, even if it's a bizarre thing to do. This is, one of the biggest results of 20th century psychology was showing that we are not nearly as rational as we thought we are. We thought we were pretty rational, and it turns out not very much. Yeah. Okay. So, but now we're getting closer to being able to explain why we're not rational at all. That's nice, right? It's great. Okay. So that was minimality. So this model helps to explain this bizarre minimality thing that if you just got a longer list for one thing than you do for the other, that equation predicts that you'll judge the apple more similar to itself than you would for the apricot. So really counterintuitive empirical finding, you find this really weird thing in the lab, and then your theory predicts it. That's really nice, right? It's a really nice bit of evidence for your theory. Also solves the symmetry problem in largely the same way, right? So you just got a longer list for apples than pomegranates. You just know more facts. More facts come to mind for apples than they do for pomegranates. That's just assuming that you're more familiar with apples than pomegranates. Then the similarity of apple to pomegranate will be different than the similarity of pomegranate to apple. Again, take a look. So it's not necessary, in this case, it's not necessarily the case if your feature list for one of those things, for A, is much longer than your feature list for B, then it's not necessarily the case that the similarity of A to B is identical to the similarity of B to A. Do check out the Smith reading if you want more details in, because he actually lays out some like example calculations here. He actually lays out some like, here's a list of features that we got people to produce in the lab. Here's why if you plug those feature lists into these similarity judgments, it produces these counterintuitive results, like the violation of minimality and the violation of symmetry. So that's good news, right? We're making progress. Okay, enough good news. Let's get back to trashing this thing. It's the more fun part, right? Okay. So we talked about these already, actually. So these came up in our discussion, which was nice. Shows me that you're getting this. Goodman's problem again. Again, we've got infinite lists of infinite feature lists. You can just generate infinite feature lists. There's no reason why you have to stop. As soon as you get people rolling on the fact that you don't have to pick out interesting or important features that are relevant to you, you can just keep generating them and generating them. So that's kind of a problem for this whole thing. Like the salience of properties is actually, for our purposes, going to be one of the most important problems here. This is kind of like, this is the bit that, remember I say this whole course is an argument? For this class, this is the most important part of that argument, which is the salience question. So, like, do you remember the homuncular fallacy? The homuncular fallacy, where in order to explain something, you posit the same facility, right? So how do I understand vision? Well, there's a little person in my head who has vision. So imagine you're trying to build a computer to run this formula, right? The similarity formula I just showed you. You're going to build an AI that can use it to make similarity judgments and then categorization judgments. This is one of the most helpful things that AI did for us, was to give us this kind of like really rigorous way of thinking about problems like this. This property F, the salience of these things, how easy do you think that subroutine is going to be to write to judge the salience of a property? Is that a short algorithm? Is that a short subroutine? Probably not. Probably not. Like, the world does not come tagged as salient or non-salient. Salience is highly context specific. The importance of something can go way up and way down depending on the situation that you find yourself in. And the ability to judge something as being salient is one of the most human level intelligent acts that you can perform. It's one that we often fail to accomplish, even at our best of even at the best of times. But there's certainly no other, there's no computer that can do this for us at the moment. This is my assertion. There is currently no computer on the planet that can take a 15-page paper and summarize it in 1 page. I'm probably going to have to change that example soon, but like, it's still the case that computers cannot work out what's important, at least partly because working out what's important depends on what you care about, and computers don't care about things. We can tell them what to care about, but it's not the computer doing the caring, it's us. So salience, the salience of the properties, is something that you need intelligence to judge, right? You need intelligence to determine how important things are. That's one of the most important things that your brain does, is figure out how important things are. So if this is an attempt to analyze cognition into its most basic elements, then we've failed. Yeah?
Let's say like a simplified model of a game. Would salience be kind of the objective to win the game, or the importance of the moves?
I think you could define salience on both levels. I think you could define salience on both levels.
With respect to the AI statement, like a computer program can't be salient in terms of like it should know to win the game, it has to be programmed to want to win the game.
Right. So what AI can do right now, really, really well, and better every year, is if you tell it what's important and what moves are available to it, it can work out what to do. So you tell it the goal is to checkmate the king. That's what you're trying to get to. Then computers are really good at, and okay, here are the moves you can make, here's your goal, go to it. The computer's pretty good at doing that. What the computer's not good at doing is working out whether it feels like playing chess, or whether chess is a worthwhile activity, or any of that stuff, right? It's not good at deciding what games to play, what rules to play by. We're the only beings on the planet, living beings are the only things that can do that right now. So by putting F in here, and actually by putting A, B, and C as well. So the same basic problem is encoded into A, B, and C. How important is the overlap relative to how important is the non-overlap? Those are context specific. It depends what you're trying to do. It depends what your value structure is, right? And so it's not a thing that you can easily mechanize. But this looks like a formalization, right? So let's think more about salience. We typically judge the salience of something against a contrast, what's called a contrast class, a set of things that it's not. There's an implicit contrast class. So ask yourself, what's similar to wood? Just off the cuff. I know this is a weird question, but what's a thing that's similar to wood? Anybody, just shout it out.
Plastic.
Plastic. Yeah, that's similar to wood. People say things like steel, concrete. Does that sound kind of reasonable? Yeah? Yeah, reasonable enough. Because there's one of the most important things that we do with pieces of wood is build things, right? So your implicit contrast class there became, as soon as we started saying things, it became construction materials. Wood is contrasted against other things that you build stuff out of. What if your implicit contrast class had been biological materials? So wood rather than soil, rather than like chitin, rather than skin and bone, right? Radically different similarity judgments. We judge salience against implicit sets of things, the salience of a given thing, and therefore how similar it is to anything, depends on implicit contrast classes. And those implicit contrast classes depend on, so the spontaneous answer was something like a construction material because we need to build things to stay alive. Again, one naked human in the wilderness is dead within the afternoon. We need to protect ourselves. We need to construct the world around us. So building things is a super important activity that we depend on and hopefully sometimes engage in, right? So the salience of wood for us depends on what kind of lives we're living. It's not a fact about wood. It's not just in the wood. It's a fact about our relationship with it. And our relationship with it is defined by all kinds of functional facts about us, what sort of lives we're living, what we care about, how we engage with our world. So salience is super hard to formalize. Super hard to formalize. Okay. And that's going to be a running theme here. Yeah.
Is that actually a problem for the formalization of similarity, though?
Hmm.
Isn't it just now we have a new problem, but it's within that formalization that we have?
So you could, I mean, in developing scientific theory, you're allowed to make that move. That's not a forbidden move. You could say, well, now we've identified the right problem, which is just working out salience or similarity so that we can figure out similarity. If what you're pitching is an analysis of cognition, that is, we're going to find for you the most simple and basic process in terms of which all other cognitive processes are going to be understood, then it's very worrying. It's very worrying because again, introspectively, categorization feels like it's not that hard. It doesn't feel complicated. It doesn't feel like it should take you deep into questions about how we sustain ourselves under late capitalism to do categorization, right? Like it shouldn't be, it doesn't feel when you're doing it spontaneously and intuitively like it involves your whole relationship with nature and society and the world. But it turns out that it does. So what we wanted was a basic cognitive process, a simple cognitive process that we could get down to we could break down into, the point here is to break intelligent looking things down into unintelligent things. Daniel Dennett says computers are an army of idiots, right? So a computer does things that look intelligent a lot of the time, but when you break it down into its parts are super, super simple. It's a switch. You know, it's a series of switches, and there's no intelligence involved in the switching. We've got it down to the point where we can break a computer down into unintelligent processes. And we were hoping that we could do the same thing for us. That's the goal here. So just to remind you all, the difference between having an analysis and having a true description. So it's perfectly possible that Smith's thing is true, that's how we do categorization, right? You have I'm not even saying he's wrong. He could be right about how we do categorization, that it follows that formula. The problem is that that's a true description and not an analysis. It's not an analysis. It's got the homuncular fallacy in it because it's assuming intelligence in order to explain intelligence. And we'll see that over and over again throughout categorization, memory, problem solving, because it's really, really hard to get under cognition. It's really challenging to forget that you're smart because I propose, again, this is one of the major results of 20th century psychology, almost everything that's happening in your mind happens unconsciously. Your mind is doing so much that you're not aware of, and because it's unconscious, it feels easy. So we keep coming to these cognitive processes and thinking, here's our candidate for an analysis of cognition. This one sounds easy. Categorization. What do? You find similar things and put them together. It's easy, right? But it keeps turning out, and it will, this is the tone and tenor of basically the first 2/3 of this course. It's just going to keep turning out that things that looked easy turned out to be really hard. Yeah?
I'm just a little confused
So this happens throughout, so they talk about implicit contrast classes in the categorization stuff. They talk about it in explanation as well. So an implicit contrast class is something like the set of things that, when you identify a thing, it's tempting, and again, in our conscious experience, it's tempting to think that you're just identifying the thing. But typically what we're doing is identifying the thing as contrasted against a bunch of other stuff. So here's my, here's a canonical joke, which is the worst kind of joke because they're never funny. So the bank robber, Willie Sutton, he went around robbing a bunch of banks and he got caught, and then a journalist was interviewing him and he asked Willie, "Why do you rob banks?" And Willie said, "Because that's where the money is," right? Ha 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 ha. Okay, so the interviewer had one contrast class. Why do you rob banks rather than getting a job or like whatever? So why do you do this? Why do you rob banks rather than doing any other number of things? And Willie Sutton had a different contrast class, which is why do you rob banks rather than robbing libraries or bakeries or whatever. So you can those are contrast classes and very typically we don't say those things out loud. You don't say what you're comparing the thing to, but very often they're active in our judgments about things. So if you ask for, you can ask for different explanations just by having different, so the same event might require different explanations with different contrast classes. So for example, why did Adam eat the apple? Here's a question. Why did Adam eat the apple? You could ask, why did Adam eat the apple rather than somebody else eating the apple? Why did Adam eat the apple rather than carving something clever into it or throwing it over the fence? Why did Adam eat the apple rather than an orange or a pomegranate? Right? So those are different contrast classes, and you need different explanations to answer those different questions because you're asking why is it this rather than this other set of things. So the implicit contrast class typically stays implicit. You don't say it out loud because usually people know what you're asking. We just sort of understand from context what you mean, kind of thing. So those are contrast classes. They're implicit because we don't say it out loud. You can say it out loud. You can say, well, why did you order the steak rather than the pasta? Then you've made your contrast class explicit. You said it out loud. Right. Yeah. Okay. Okay, so this stuff about salience is probably the most important thing that we've talked about today. That's the thing that's going to be the continuing theme going forward. I got a bit more stuff, a bit more misery to heap on the resemblance theory, and then we'll call it a day. So do keep this salience stuff in mind. Again, that's the continuous thread, the argument going through this course. But we're also doing a survey of the important issues. So we're just going to do a bit more of the history of this stuff to round this discussion out. So let's talk a little bit more about problems for the resemblance theory. So Lance Rips, the psychologist with the greatest name in the history of psychology, tries to show in this 1989 paper, it's called a double dissociation between judgments and categorization judgments and similarity judgments. So Smith is pushing this view. He says similarity judgments drive categorization judgments. He says similarity judgments underwrite categorization judgments. They cause categorization judgments. And what Rips is going to try to do is show a double dissociation between similarity judgments and categorization judgments. So you can have differences in similarity, but make the same categorization. You can have differences in categorization, but make the same similarity judgments. And when you're trying to trace out the causes of things, of course, a double dissociation is the gold standard for showing that one thing doesn't cause the other. So if you can change x without changing y, and change y without changing x, then you've shown a double dissociation between x and y. You've shown that there's no causal relationship between those two things. Because of course things can be correlated without being causally related. Here's my favorite example in the world. This is the global average temperature going on a rising tide, which is the doom of us all. This is the number of pirates in the Caribbean. Now, as you can clearly see, as the number of pirates in the Caribbean goes down, this is the largest value and this is the smallest, global average temperatures have gone up. It's a fairly tight correlation. Okay. So here's my policy initiative. We need to get piracy going again in the Caribbean, and that will solve the climate crisis and save us from our own well-deserved destruction. Probably not, right? Because you could change the number of pirates in the Caribbean and it wouldn't change global average temperature. You could change the global average temperature, it probably wouldn't change the number of pirates.
Is that the number of pirates from 35,000 to 45,000?
Yes, it does. Yes, it does. This is not the most scientific graph you'll see all day. Yeah, no, you read it right. You read it right. Another helpful point to keep in mind, check the axes, because there's nothing a priori wrong with this. It's just incredibly deceptive. Right. And this one goes from 400 to 17 for some reason. Anyway. Okay, the point being is there's a rough linear correlation between these. The point being, if you can change one thing without changing the other, you change the first thing without changing the other one, what you've shown is a double dissociation. You've shown that even if two things are correlated, there's not a causal relationship between these two things, which is what Smith is suggesting. He's suggesting there's a causal relationship. There's a driving relationship between your similarity judgments and your categorization judgments, with your similarity judgments being the kind of origin, the thing that runs the show, right? Similarity judgments are the basic elements that drives categorization judgments. So here's two experiments that RIPS does to try to show this double dissociation. Okay, so within category variability, he gives people this description. Consider an object which is round and 3 inches across. You got this in mind? That's what the only description he gives them is just this round, about 3 inches across. And he asks them the following question. Is that more similar to a pizza or a quarter? What do you think? Is that more, is this 3-inch round object more similar to a pizza or a quarter? Most people said quarter. Sometimes I will be trying to trick you. This is not one of those cases. Most people said it's more similar to a pizza than a quarter, because a quarter is like 1 inch and this is just 3 inches, so it's not that different. Whereas pizzas are supposed to be large, right? If somebody gives you a 3-inch round pizza, you'll be disappointed. You'll be mad at them. Hey, I brought you a pizza. So people's similarity judgments tend to say that this 3-inch object is more like a quarter than a pizza. That's on average what people said. Now, is this 3-inch object, he asks them, that's the similarity judgment. Now he asks them this categorization judgment. Is our 3-inch object more likely to be a pizza or a quarter? Now what do you think? Pizza. I'm hearing pizza whispered. It's making me hungry. Okay. Why is that? Why do people overwhelmingly say it's more likely to be a pizza than a quarter? Yeah.
Quarters are all the same, whereas pizzas are varied.
Right. If somebody gives you a 3-inch wide object and says, here's a quarter, you say, no, that's not what quarters are like. Right? You will just deny that that's a quarter at all. And you should do, because the category of quarters is fairly well specified. They're about this big around. Whereas pizzas, there's nothing intrinsic to the category of pizza that says they can't be 3 inches. Actually, I grew up on pizzas that were maybe like this big. They put them in the microwave. They were terrible. But bagel bites, yeah, you can have little tiny pizzas. If somebody brings you one, you're sad because there's no good tiny pizzas. But like a regular pizza is far superior. But like if somebody hands that to you, you're not like, that's not a pizza. You're like, that's a very small pizza, and I'm sad about that, right? So there's a size constraint built into the quarter category, but there's no size constraint built into the pizza category. You could have a pizza that's 10 feet wide. You have a pizza that's 3 inches across. Those can both be pizzas. Okay, so what just happened there? Well, you've got a similarity judgment that cuts one way using the same stimuli. So you got people imagining a quarter, a pizza, and a 3-inch object, and you've got similarity judgments cutting one way and categorization judgments cutting the other way. Right? So you can change. It's weird to call it change, but it's just sort of under different conditions, people will make different judgments. If similarity drove categorization, if similarity was what underwrote categorization judgments, you shouldn't be able to get people to make similarity judgments in one direction and categorization judgments in a different direction, right? We're dealing, it's the same two categories and the same one object, right? So we're holding constant the categories that we're dealing with, and we're just asking people to make one of two different judgments: similarity judgments, categorization judgments. And if similarity drives categorization, they should make the same judgments. Whereas in this case, they don't. Yeah? Okay, so that's one half of the dissociation. Okay with that? Okay, let's do the other half. So now we're going to tell the story of the sorp and the dune. Let me get this. I wrote this down because it's. Did I write this down? Ah, yeah. Okay. So we got a sorp. A sorp is an animal. It's running around on two legs. It's got two feathery wings. It eats mostly seeds and berries and lives in nests high up in a tree. However, our sorp is unfortunate because it lives near a chemical plant, and then due to exposure to the chemicals, it slowly loses its feathery wings and instead grows wings composed of a transparent membrane. It develops a brittle, iridescent shell and grows more legs. It sustains itself almost entirely on the nectar of flowers. However, when it mates with another sorp, who apparently has low standards, it has regular sorp babies. Now, is that thing a bird or an insect? The original one, the one that turned into, so it lost feathery wings, it's got transparent wings, it's got an iridescent shell, it's got a bunch of legs. Yeah.
Bird was the same species?
That's what most people say. That's what, I don't think there's a right answer here, but that's what most people say. Yeah, yeah, yeah.
This one kind of begs the question of like how many features or ways that we define something can be ripped away from it before it's no longer defined as that thing.
It does. It absolutely raises that, and that's precisely the question Lance Rips wants to raise here. Yeah, yeah. So, despite radical feature-level dissimilarity, everything that you normally associate with birds has been taken away from our poor sorp. But nonetheless, people overwhelmingly categorize it as a bird. One of the reasons being, I think, that we structure our categories around species concepts. Okay. Now the story of the dune. So the dune, I didn't write down the story of the dune. Oh no. All right, I think I can reconstruct it from memory. So, can I? Oh God. The dune. Oh no. Right, so the dune goes through a natural life cycle, right? It's not exposed to chemicals. Starts off with two feathery wings and runs around on two legs. It usually, sort of as part of its natural maturation cycle, loses its feathery wings, gains transparent membranous wings, grows a bunch of legs, has an iridescent shell. That's the story of the dune, as I recall. Okay, and when you ask people, is that thing a bird? They go, no, it's an insect. Okay, so what's happened here? So the SORP changes properties by accident. And people still want to categorize it as a bird because it just happened to live near a chemical plant. So people are happily willing to massively override the normal feature list that you associate with birds. They'll override that because no, that was all just this weird accident that it happened to have to go through. Whereas the dune, we say, no, that's its normal life cycle. You're an insect. So now we've got we've got people who are willing to just ignore the similarity, right? So we're making categorization judgments that absolutely fly in the face of our similarity judgments. Right? We don't care about the similarity judgments when we're making this categorization claim. We, the people who in 1988 who we had in his lab. But let's assume that it generalizes to all of humanity, because that's how psychology works. Okay. So the point being, you can get people to make categorization judgments that absolutely ignore their similarity judgments, right? In the story of the SORP, people were perfectly happy to say, no, I don't care that doesn't have feathery wings. I don't care that it has a bunch of weird legs. I don't care that it's got an iridescent shell. What I care about is that its species, its category is bird. Okay, so that's supposed to be the double dissociation. So we can, given these facts, you can sometimes change people's categorization without changing their similarity judgments. And you can change their similarity judgments without changing their categorization judgments. You can pull these two types of judgments apart under frankly given slightly weird scenarios, but nonetheless, you can cause people to make radically different categorization similarity judgments. What we said before was, if you're looking for a causal relationship, if you can do this double dissociation thing, what that shows you is that's not a causal relationship. So it's simply not the case that similarity judgments are driving categorization judgments at least in a one-directional way. This doesn't show that they're unrelated, right? But what it shows is we can't do this thing that we really wanted to do. What we really wanted to do was identify a simple, basic cognitive process, similarity judgments, that explains categorization, and then categorization would explain the rest of cognition for us. That's what we wanted. That's what it would have been nice to get. What this double dissociation shows is that at minimum, categorization judgments are affecting our similarity judgments as well. So at minimum, we've got a loop here, right? If not, a much more complexly embedded network of causes that simply just hasn't yielded for us a nice, neat, simple analysis. So, okay. So that's the response to Smith. So far we've seen the geometric account. We've seen some criticisms of it. We saw Tversky's account, a way of formalizing similarity. We saw some advantages of it. We saw some criticisms of that. And then we've got Rips doing his criticism. So Smith, like a good scientist, again, I told you this was going to be a story of failures. Like a good scientist, Smith actually pays attention to this criticism. Smith tries to respond and come up with a way of changing the theory to respect what the facts are saying. So he tries to make the following distinction. So this is Smith's response to the criticism from Rips. This fairly long dialogue, this class. So he tries to make a distinction between two types of similarity, or two types of categorization, sorry. Similarity-based and rule-based categorization. right? He says this stuff with the sorp and the dune, this stuff with the pizza and the quarter, these are examples of the limits of my theory. So he admits, my theory is shown to have limits. What my theory can handle, he thinks, is the similarity-based cases. So it's this resemblance theory of categorization. So he thinks that his theory can handle perceptual facts. The categorization is based on perception, but that there's another kind of categorization that's based on rules. This is his move. And it's a concession. It's a real concession, right? He's kind of ceded a whole bunch of territory. He says, he started off by saying, here's my theory of categorization. Here's my theory of how we do all categorization. He's had to admit that there's at least a class of categorization that he can't explain with his similarity-based theory. He still wants to say that the similarity-based theory is the most basic form of categorization. So before you can learn rules in the sense of explicit formal rules that people explain to you, of course you're a little kid and a baby before that who can only do perception, right? Before you have language, you have perception. That's how you get your whole cognitive ball rolling. So he thinks his similarity-based thing is still the more basic one, but that there's also, okay, Rips, you've shown me that my theory is not complete. There's also this rule-based thing. Okay. So, and he gives some examples. So similarity-based is based on perceptual differences. It's what you can see. And he gives examples like, you know, when we categorize birds, we have things like that they fly, they lay eggs, they sing, they nest in trees, they eat insects. Things you can see. And then rule-based are things like quarters are only ever an inch across, that kind of thing. Okay, does this worry anybody? No, we're all good with this? It's all fine? Okay. Okay, well I'm gonna dump on it then because that's fun for me. Okay, so here's a worry about this thing. One, that he's got no account of rule-based categorization to offer us. So basically he's given up half of the categorization. But here's a worry. It doesn't seem that easy to distinguish between similarity-based and rule-based categorization. Like, just for example, I mean, I've seen birds fly. I don't think I've ever in my life seen a bird actually lay an egg. Right? Hopefully some of you have. Some of you are more in touch with nature than I am. But I've never seen a bird lay an egg. Possibly never seen it eat an insect either. I certainly didn't get the category of bird from watching a whole bunch of birds lay eggs. That's just not how it happened for me. But these are the examples that he gives. I didn't generate these examples. These are the examples he gives of things that are just easily accessible to perception on the basis of which we categorize things. And I am very doubtful that these are all things that are easily accessible to perception. I certainly didn't learn that most birds lay eggs via perception. I have never even seen most birds. I'm sorry, I'm not a very worldly man. Most birds I've never seen. That's not how I got that category. I got it by somebody telling me about birds. So it's just really unclear how to separate the perceptual from the stuff that's been explained to you, for the rule-based or inferential. Those two things really see, and I think we've seen a couple of examples of that this class, like for example, how similar are water, light, and sound? Well, now that feels a bit perceptual to me. It feels a bit perceptual. Once you've got the rule, you see things differently. Right? Like you can, once you've learned some rules about how things work, it can actually transform the way you experience the world. Like you see a bird, a sparrow and a flamingo as being similar. You look at them and you're like, oh yeah, those are similar. They're birds. And you focus in on, your perceptual awareness is not just taking in information. It's of course selecting what's important from that information, right? This is the salient stuff where you hone in on the information that you have available is vast beyond comprehension, and you are constantly under the pressure of figuring out which bits of it are important, and that's often scaffolded or helped out by having rules. So the rules guide your perception, and of course the perception guides the rules. So these two categories are very difficult to tease apart. Very difficult. Okay. All right, so let's leave that there. Some quick notes about thinking about what we've done today, and then we'll call it a day. One of the things that I hope came through here is that common sense is often the enemy of doing this work. Common sense can mislead you because common sense presents you with a finished product. Like your common sense experience of your own perception, what you're getting is a finished product, not the process that brought you to that product. So you can mistake features of that extremely polished, carefully crafted and constructed sensory experience that is your conscious experience of your life, thinking that you know how it all works. And that's seemed to get us into trouble. So I propose that this is part of what got Smith into trouble, was thinking that similarity is easy. Similarity is transparent, because it's transparent to us. From the first person perspective, similarity judgments look like they are easy, and it turns out that they are not. And that philosophy can help. Philosophy is a very annoying practice where somebody comes along and picks away at your basic assumptions that you were perfectly fine with. You had no problems with those assumptions. It wasn't causing you any difficulty. If it caused you real difficulty, you would have dealt with it in some explicit way already. But some philosopher comes around and says, what do you mean by similarity? Huh? What do you mean by that? Tell me what you mean. And it says something about philosophy that our most revered hero is Socrates, who was so annoying that they killed him. And the lesson that we took from that was not to be less annoying. But hopefully you can see, if your problem is specifically that common sense and unexamined assumptions are tripping you up, suddenly philosophy seems like it might be a useful tool here. So doing this fairly irritating practice of digging into perfectly fine seeming assumptions can help us get out from under the things that should be, you want to be looking at something rather than through it. Another thing to pick out here, having a formula does not mean that you've formalized something. So I showed you a formula. Those of you who are humanities people probably had the experience of most humanities people, which is your brain just locks up. Okay, that must be right. It's math. It must be right. Those of you in sciences didn't have that experience, but you also don't have the training at explicitly and carefully interrogating the assumptions of the things you're being presented with, because mostly scientists are trained from textbooks where they tell you true things rather than telling you things that you need to question. So keeping in mind, somebody presenting you with a formula doesn't mean that there's no little homunculi running around in it. You can have something that looks perfectly formal, but actually have deep, important problems in it in the form of unformalized elements of that formula. That's why artificial intelligence is such a powerful methodology for asking questions about this stuff. Because you can't trick a computer. You cannot trick a computer into thinking that you formalized something when you actually haven't. The computer just won't work, right? Your program just won't work. If you think you formalize something, try to build something that can do it. And very often, we'll look at the history of artificial intelligence in a couple months, very often you just find out that you didn't know how to do it in the first place. That's generally what happens when you try to take it from the step of formalizing to mechanizing. That's why mechanization can help. Okay, enough for today? Okay, see you on Tuesday.